So this is chapter 2, which is our first chemistry chapter in unit 1 of Bio 1. So we're going to talk about molecular formula, subatomic particles, isotopes, electron shells, a little bit about the periodic table, different kinds of chemical bonds, chemical reactions, polar molecules, properties of water, solutions, what dissolves in water, and pH. So you might be thinking to yourself, like, I thought I was in biology, or maybe I didn't want to take chemistry, so I took biology instead. But biologists really need to learn and understand chemistry. Why do you think that is? So biologists need to have an understanding of chemistry, right? Because if we go back to that level of organization thing that we talked about in chapter 1, right, we've got atoms that form molecules, and then molecules interact with each other in special ways to form organelles, and organelles are parts of cells, and kind of so on and so forth there, right? So we are made up of chemicals. Also, things like hormones or neurotransmitters, those are chemicals, and proteins that act as receptors, also part of chemistry. So biologists really need to have a decent understanding of chemistry in order to make biology make sense. So with molecular formula, that contains the chemical symbols of the elements in the molecule. The subscript, which is the little number like C6, the 6 is the subscript, that indicates how many of each atom are present. So H2O is water, and there's 2 hydrogens and 1 oxygen. A molecule is when you have 2 or more atoms that are hooked together. So hydrogen gas, H2, or water, H2O, would be a molecule. And then a compound is any molecule composed of 2 or more elements. So nitrogen gas, N2, and oxygen gas, O2, are examples of molecules that are not compounds because there's only one element in those molecules. That's not something I'm really going to dig deep into on the test, though, so don't worry about that too much. But if you're just kind of wondering what's the difference between a molecule and a compound, there it is. Atoms, then, are the smallest stable unit of matter, and they are made of subatomic particles. So the center of the atom is where the nucleus is, and the nucleus is made up of protons and neutrons. Neutrons have no charge and a mass of 1 atomic mass unit, right? Neutron, neutral, no charge. Protons have a positive charge and also a mass of 1 atomic mass unit. Electrons are found outside of the nucleus, and it kind of depends like what level of chemistry you're at, whether you say, oh, they're found in orbitals or electron shells, right? Bio 1, we'll just say they're not in the nucleus. Electrons have a negative charge, and they're really small mass, so we'll say it's effectively 0 atomic mass units. Protons and electrons are present in equal numbers, so that would give an atom no net charge. And then the number of neutrons can vary. So isotopes are forms of an element that differ in the number of neutrons they have. So on this slide, there's pictures of different isotopes of carbon. So all of those isotopes of carbon have 6 protons because that's what makes it carbon, but they have different numbers of neutrons. If you look at the first one, carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons and 7 neutrons. Carbon 14, 6 protons, 8 neutrons. Radioisotopes can decay spontaneously and give off particles and energy. And we can use radioisotopes for things like carbon dating of fossils, medical imaging, and even tracing food through the food chain. If you feed one organism more of a certain isotope, the carbon of that particular isotope is incorporated into their body, and then when something eats that organism, they get that isotope, and so on and so forth, kind of down, or rather maybe up the food chain. So then if we look at the periodic table, you can see on this example there, I've highlighted the atomic number and the atomic mass. So the atomic number is the number of protons in the nucleus. So it's that whole number on the periodic table. The atomic mass is the average mass numbers of all of the isotopes of an element. Remember, isotopes can have different numbers of neutrons. So the atomic mass is always going to be more than the atomic number. And the mass number is the mass of protons and neutrons of a particular single atom. So mass numbers of atoms of an element are not all identical because, again, there's different isotopes of that element that could have different numbers of neutrons. So let's review which subatomic particles are located in the nucleus of an atom. That would be protons and neutrons. And then number 2 says, which element would have 6 protons? Maybe some of you have memorized that in high school chemistry or something. What tool could you use to find that out? I would say the periodic table, right? And then what number on the periodic table would tell you how many protons are in that particular element? So that would be the whole number on the periodic table. So which of those has a whole number that's a 6 on our periodic table? That's going to be carbon here. So carbon has 6 protons. So energy then is the capacity to cause change. And we'll talk a bit more about energy later in, I think it's chapter 5. And potential energy is energy due to location or structure. So this is relevant to this chapter because our electrons in our atoms are found in different electron shells, and electrons have energy in part due to the distance from the nucleus they're at, and the energy level of each shell increases as the distance from the nucleus increases. So electrons can move to higher or lower shells by either absorbing or releasing energy. So the periodic table is arranged to show the electron distribution of the elements. So if we look at the rows and columns, I know they're not called rows and columns in chemistry, but if we look at the rows and columns, the first row has 2 columns in it, and there's space in that first electron shell for 2 electrons. The second row has 8 columns, and there's space in that second electron shell for up to 8 electrons. And the third row also has 8 columns, so there's space in that third electron shell for 8 electrons as well. So when we look at the periodic table of elements, in chemistry you're going to go over it in a lot more detail, but this is really all that we're going to focus on in biology for this point in time. The chemical behavior of an atom is determined by the distribution of electrons in the electron shells, in particular the electrons in the outermost shell, which is called the valence shell, is important. When atoms have incomplete valence shells, they are going to share or transfer electrons with another atom, and that will bring those atoms closer together. So that results in chemical bonds. The types of chemical bonds we'll talk about today are ionic bonds, covalent bonds, including polar and nonpolar covalent bonds, and hydrogen bonds. I put a little asterisk by hydrogen bonds because hydrogen bonds don't involve sharing or transfer of electrons. Rather, it's more of a weak association, and we'll get into that more coming up. So when we look at elements, chemically inert elements are stable and unreactive because that outermost energy shell is fully occupied or contains 8 electrons. These guys are found in the last column on the periodic table. They're the noble gases. They're called noble because they don't participate in chemical processes. So here in this slide, we've got helium on the left-hand side. It's in that first row on the periodic table, so it can only hold 2 electrons in its outer shell. In the second image, we've got neon, and neon can hold 8 electrons in its outer shell, and both of those outer shells are full, so these are chemically inert elements. With chemically reactive elements, their outermost energy level is not fully occupied by electrons, so these guys are going to gain, lose, or share electrons, which is really just forming bonds. And they do this to achieve stability, and once that outer shell is full, the atom is stable. So on the bottom of this slide, we've got hydrogen on the left. It has 1 electron in its shell. Since it's that first shell, it can only hold 2 electrons, so it would need 1 more electron to be stable. Carbon is the second atom pictured. It's got 4 electrons in its outer shell. How many more does it need to be stable? It would need 4 more. Oxygen is our next picture, right? Oxygen's got 6 electrons in its outer shell. It would need 2 more to be stable. And then the last one, we've got sodium. Sodium is a little tricky, right? Sodium has only 1 electron in its outer shell. And, there's more rules in chemistry that they'll give you about this, but if you just think about, like, in your life, is it easier to toss one thing away that you don't need or find 7 more things that are matching? It's easier to just kind of toss one thing away. So what sodium actually does is it gives away that electron. So then its second shell becomes its outer shell, and that is fully occupied with 8 electrons. So ionic bonds are created by the kind of electrical attraction between a cation and an anion, or another way to describe this is the transfer of electrons from one atom to another. If you go back to that first sentence and you're like, what is a cation and an anion? So an anion is when an atom has gained an electron. So that gives an atom a negative charge, right? Because what's the charge of an electron? That would be negative. So when it gains an electron, it gives the atom a negative charge. A gain of 1 electron gives a negative 1 charge. A gain of 2 electrons would give a negative 2 and negative 3 and 4 and so on there. A cation is when an atom has lost an electron. So again, that charge of the electron is negative. So when you lose a negative thing, that's actually a positive. So it gives the atom a positive charge because it still has those protons in the nucleus. So losing 1 electron gives the ion a +1 charge. You could lose 2 electrons and get a +2, lose 3, get a +3, and so on there. So this is just a picture of a chlorine atom gaining an electron and becoming a chloride ion. Again, when you take chemistry, you'll go over more details on how we name these sorts of things, but there's chlorine atom gaining an electron and becoming the negative chloride ion. And this next one, we've got sodium atom losing an electron and becoming a sodium ion, which is a cation. And I bet that meme here with the cations are positive is probably older than you are, but it's a good one. It's a classic. Like, it's a vintage meme at this point, right? So the joke is, right, cations are positive, like cats have paws. Jokes get funnier the more we have to explain them. So we've got our positive sodium cation there and our negative chloride anion. So the opposite charges attract to each other. We've got an ionic bond. So now we have sodium chloride, which is just table salt there. And they're showing you in this picture on the slide that kind of crystal structure that you're probably familiar with if you've ever looked closely at a grain of salt. So another kind of bonds are covalent bonds. Covalent bonds happen when atoms share valence shell electrons, and that happens between atoms that have similar electronegativity values. If we look at the root word co means together, right? Like you could cooperate, like cooperate. You could cohabitate, so you're sharing your habitat, right? So covalent, they're sharing valence shell electrons. So this has to happen between atoms that have similar electronegativity, because atoms with similar electronegativity have a similar pull on their electrons, so they're more able to share. Like, one is not taking the electron from the other, they're sharing it. So covalent bonds allow atoms to fill their valence shell at least part of the time. So you could have single covalent bonds where there's 1 electron from each atom shared, or double covalent bonds where there's 2 electrons from each atom shared, or triple covalent bonds where there's 3 electrons from each atom shared. So if you've ever shared something with anybody ever in your life, right, sharing is not always equal. There's equal and unequal sharing. So nonpolar covalent bonds are when there's equal sharing of electrons. This happens when atoms have very similar electronegativity values. So any atom that's bonded to itself, like H2 hydrogen to hydrogen, or O2 oxygen to oxygen, or something like methane, because carbon and hydrogen have very similar electronegativity values. I always think of my brother when I talk about polar covalent bonds, because like we did not equally share everything as kids, right? So polar covalent bonds are when there's unequal sharing of electrons. The electrons spend more time with one atom than the other, because one atom has a tighter hold on those electrons than the other. Hydrogen bonding is the last kind of bonding that we're going to talk about. It's not really bonding in the same way as the other types of bonds were, though, because there's not a transfer of electrons or a sharing of electrons. Hydrogen bonding happens when a partially positive hydrogen atom is attracted to another atom that has a partial negative charge. This is different than ionic bonding because these atoms don't have a full positive or full negative charge. These partial differences in charges are due to unequal sharing of electrons. So in our picture here, we've got water molecules, and these water molecules here, right? This is that's a water molecule. So this dotted line here is a hydrogen bond between the partially positive hydrogen and the partially negative oxygen on the other atom. In the other picture here, we have a water molecule with that partially positive end attracted to the partially negative end of this nitrogen on the ammonia. Nitrogen is partially negative because the nitrogen has the electrons more than the hydrogen does in this ammonia molecule. So hydrogen bonds are important in biology because they can pull molecules closer together, and it can change the shape of a molecule. Later we'll talk about proteins, which are really large molecules, and they fold up together with hydrogen bonds. And later in this chapter, we'll talk about the properties of water, many of which are due to the hydrogen bonding between water molecules. So that molecular shape is really important. Remember in chapter 1, we talked about structure and function going together. Same deal here. Molecular shape really does matter. The biological molecules can recognize and interact with each other because of molecular shape, right? So if we have let's say an endorphin receptor, right? It can bond with natural endorphin, or it could bond with morphine because of that chemical structure that's highlighted on both of those molecules. So the receptor can bind to particular molecules because of the molecular shape. So that brings us to chemical reactions. Broadly speaking, cells stay alive by controlling chemical reactions. Reactants are the reacting substances, and they react together to form products. So in chemistry, you'll probably spend a good amount of time balancing equations. You need to have the same number and kinds of atoms going into the equation as coming out of the equation. So an unbalanced equation would be like H2 plus O2 gives you H2O. That's not balanced. You've got 2 hydrogens going in and 2 hydrogens going out, so that's okay. But you've got 2 oxygens going in and only 1 going out, so we can't just lose that oxygen. A balanced equation would be 2H2 plus O2 gives us 2H2O, because we have 4 hydrogens going in, 4 hydrogens going out, 2 oxygens going in, 2 oxygens going out, so that's balanced. But again, for our class, you don't need to worry about balancing the equations specifically. I just want you to know equations need to be balanced. In chemistry, you will have plenty of time to go over that. Our book doesn't actually talk about the rate of chemical reactions, but I do think understanding how the rate of chemical reactions can be influenced is important, because living things stay alive by controlling the rate of chemical reactions. So if we think kind of broadly about what happens in a chemical reaction, you've got different particles moving around, and basically they bump into each other. And when they bump into each other, they either share or transfer electrons, right? So form bonds. So if we increase the temperature of a reaction, that increases the rate of the reaction, because the particles are moving around faster, and if the particles are moving around faster, they are more likely to bump into each other. If we decrease the particle size of our reactants, that's going to increase the rate of the reaction. If we decrease the particle size, the particles themselves are going to be moving faster, and that increases the rate. If we increase the concentration, that's like the number of particles per unit area, so like the amount of stuff. If we have more particles in a particular area, they're more likely to bump into each other. So again, that's going to increase the rate of the reaction. Then later we'll talk more about enzymes and catalysts, but catalysts increase the rate of a reaction without being chemically changed, and enzymes are typically proteins, not always, but typically proteins, and those are biological catalysts. I think people have probably heard about like digestive enzymes before that help you break down your food. So really, chemical reactions are reversible. The products of the forward reaction become the reactants for the reverse reaction, and chemical equilibrium is reached when the forward and reverse reaction rates are equal. So let's review here. So which of the following could represent a chemical reaction? You might want to pause this and kind of look at this to figure this out, but in the picture, each of the different colors are supposed to represent a different kind of atom. So again, pause it if you want some time to think this through. Let's go through each of these and see if they could be a chemical reaction or not. So if we look at A, on A, do we have the same thing going in to the reaction as going out of the reaction? No, we do not. So it can't be A, because like we don't have 4 white circles going in and 4 white circles going out. So not A. What about B? Okay, so B, we have the same stuff going in as out, right? So 4 white circles over here, 4 white circles over here, 4 light grays, 4 light grays. But did anything change? Were any bonds broken or rearranged? No. So it can't be B. If we look at C, got 4 white circles going in, 4 white circles going out. That's good. 1 black dot going in, right? 1 black dot going out, 4 light gray, 4 light gray. That's good. And did they rearrange? Yes. So, okay, C's our answer, but good test taking strategy. We should always look at all of our options before we just decide, because maybe we misread something or made a mistake. But if we look at D, what do? They just like colored in everything to make it darker, so not D. Number 4 says, which type of bonding involves the transfer of electrons? So we talked about hydrogen bonds, covalent bonds, and ionic bonds. So that's going to be ionic bonds. I got a pen, but my handwriting is still terrible. Ionic bonding is transfer of electrons. And then how is hydrogen bonding different from covalent bonding? Hydrogen bonding is a weak attraction, and covalent bonding is sharing of electrons. Sharing electrons. Okay. So that brings us to polar molecules. With polar molecules, the spatial arrangement of polar covalent bonds and how the electrons are distributed in a molecule can result in a molecule being a polar molecule. So water has both polar covalent bonds and the entire molecule, because of the shape of the molecule and distribution of electrons, makes it a polar molecule. So the entire molecule has a slightly negative end and a slightly positive end. So number 6 says carbon tetrachloride has polar covalent bonds, but it's not a polar molecule. Why is this? So if we look at this carbon tetrachloride, the carbon has a partially positive charge, and all the chlorines have slightly negative charge or partially negative charge. But the slightly positive carbon is in the middle, and it's surrounded by all of these chlorides here. And so these chlorines with a partial negative charge on the outside, it's hard to tell, but these are supposed to be like in 3D space, right? So there's not a slightly positive end and a slightly negative end of the entire molecule, because the entire like outside portion of the molecule is slightly negative. So there's polar covalent bonds, but the molecule is not polar itself. I'm not writing that with my pen. It's not going to work for us. Sorry. So replay it if you have to. Number 7, in a water molecule, where do the electrons spend most of their time? So on the water molecule, this blue guy is the oxygen, and these red guys are the hydrogens. So the hydrogens have this partially positive charge. The oxygen end has this partially negative charge. What's the charge of an electron? Negative, right? So the electrons are going to spend more time on the oxygen side of the water molecule. So water has some very unique properties that other molecules don't have, and these properties of water make life possible on Earth. So most living things are roughly 70% water, and those water molecules are polar. So that leads us to these properties of water. So we're going to talk about the properties more on the next slides, but it's nice to have them all in one space, right? So water has cohesive behavior. Water has the ability to moderate temperature. Water expands when it freezes, and water is a good solvent. So water has cohesive properties. Cohesion means water molecules stick together, right? They stick together with those hydrogen bonds. They are also adhesive, meaning they stick to other polar molecules or surfaces. This adhesion picture comes from like water being transported in plant vascular tissues there. So that's why that water molecule is holding on to a little green diamond there, because it's supposed to be plant vascular tissues. With that cohesion and adhesion, there's also surface tension, which is a measure of how hard it is to break the surface of a liquid. So water molecules at the surface of water cling more tightly to each other than they do to the air above it. If you ever stick your finger in water, there's like a little droplet that will form on your finger because those water molecules are holding on to each other. It also allows light insects like this water strider to walk across the surface of water. Water is also able to moderate temperature. Water has a high specific heat. There's lots of those hydrogen bonds that are linking the water molecules together, and that allows them to absorb heat without greatly changing temperature. You know this if you've ever tried to boil water before, right? Like there's the old saying, like a watch pot never boils. It's not that it never boils, but it takes a lot of energy input to make that water boil. So that temperature of water rises and falls slowly. Water also has a high heat of vaporization, meaning, again, it takes a great deal of energy to break those hydrogen bonds for evaporation to occur. So heat is actually dispelled as water evaporates. You know this because you sweat, and generally speaking, when you sweat, it cools your body down. So another property of water is that water expands on freezing. So water is more dense at 4 degrees Celsius than it is at 0 degrees Celsius. So most substances actually contract and are more dense at lower temperatures, but water is the opposite. It is less dense at lower temperatures, which you know this, right? Ice floats. But that is really a cool property of water because ice can act as an insulator. So large bodies of water can have this ice surface layer where organisms can live above it and under it, and that ice insulates the water below, so the water, if it's a large enough body of water, doesn't freeze solid. Water is also a good solvent. So water is the dissolving agent for many solutions, right? In our bodies, again, we're roughly 70% water. We've got different things dissolved in our blood. So a solution is a homogeneous mixture of substances, so it's evenly mixed. The solvent is the dissolving agent, and water is the solvent of life. And the solute is the substance that is dissolved in that solvent to make a solution. If we were making a salt water solution, the salt would be the solute, the water would be the solvent, and the solution would be salt water. So most chemical reactions in organisms involve solutes dissolved in water. Like if you've heard of your blood glucose levels or your blood sugar levels before, the glucose is dissolved in your blood, which again is mostly water. So what actually dissolves in water? Inorganic compounds with ionic bonds are good at dissolving water. So water molecules actually surround those ions. The anions are surrounded by the partially positive poles of the water molecules, because what's the charge of an anion? Negative, right? So the positive portion of the water molecule is going to surround that. Cations, what's the charge of a cation? And I'll put up your paws, right? Positive. So, because cats have paws. So cations are surrounded by the negative poles of the water molecules. So these water molecules separate those ions and surround those ions, right? If you put salt into water, those salt crystals dissolve in the water. Some organic compounds can also dissolve in water. It really depends on the structure of the organic compound itself. So if you've ever made like a protein shake before, right, a protein is an organic molecule, and right, depending on what brand of protein powder you're buying, some of those dissolve better in water than others. But things that dissolve in water are said to be hydrophilic. Hydro meaning water, philic meaning loving. So they get surrounded by water and dissolve in water. So here's just a picture to show you those hydration spheres and the water molecules surrounding the sodium and chloride in that beaker of water. The other one is showing you a glucose molecule, so a sugar molecule dissolving in water. That second picture is not as great because it only has one glucose molecule. But if you imagine like a sugar cube and putting it in water, right, it would no longer be a sugar cube. Or even just like a grain of sugar, if you put that in water, those sugar molecules and that grain of sugar would dissociate and be surrounded by those water molecules. So not everything dissolves in water though, right? Some things are hydrophobic. Hydro meaning water, phobic meaning fearing. So things like oil would be hydrophobic, right? Oil and water don't mix. So that would be an example of something that's hydrophobic. This picture is showing you, proteins, which are large molecules, and some of those do dissolve in water. Those are those big purple chunks there in the picture. And then fats and oils are not readily interacting with the water. So the fats and oils are hydrophobic. Number 8, assume you're making a Kool-Aid solution. So label the solution, solute, and solvent in our picture here. So if we're making a Kool-Aid solution very scientifically, in our first beaker here, we have water. What's the water? That's going to be the solvent. And then this is our Kool-Aid powder here. So that's going to be our solute. And then the last beaker, we have the mixture. That's the solution. So that brings us to acids and bases. Pure water ionizes to a very small extent into hydrogen ions and hydroxide ions. So H2O splits into H plus and OH negative. And again, in chemistry, you're going to go into more details on this, but acids are molecules that release hydrogen ions into solution. A strong acid releases more H plus than a weak acid, and bases lower the concentration of hydrogen ions. They either release hydroxide or bind to H plus, because releasing OH negative means they'll pick up more H pluses. In our pictures here, we've got an example of hydrochloric acid as our acid, and sodium hydroxide down below as an example of a base. So pH is actually the negative log of the concentration of hydrogen ions in solution. A neutral pH around pH 7 has an equal concentration of hydrogen ions and hydroxide ions, right? Because H plus OH negative is H2O or water. If we go above 7, we're dealing with alkaline or basic solutions. They actually have a low concentration of hydrogen ions because, again, it's the negative log of the concentration of hydrogen ions, and a higher pH. And we're not tasting chemicals, but alkaline solutions have a bitter taste. If we go below 7, those are acidic solutions. They have a high concentration of hydrogen ions and a low pH. And again, generally speaking, we're not tasting chemicals like in the lab, but lemon juice or citric acid, those are acidic. Those are acids, so they have a sour taste, and that would be okay to taste those sorts of things. But definitely don't go tasting, 1 molar hydrochloric acid. That would be a bad thing. So why does pH matter to biology? Well, the pH of a solution can affect the shape and function of molecules. It can affect the rate of chemical reactions. It can affect what molecules can bind to each other and even what can dissolve in water. So in living things, we actually have buffer systems to help resist pH change. And there's buffers in chemistry as well, not just in living things, but buffers help resist pH change. So strong acids and bases then are going to completely dissociate in water, like hydrochloric acid is a strong acid. You put it in water and it breaks apart into hydrogen ion and chloride ion. Weak acids and bases, on the other hand, like carbonic acid, that H2CO3 there, that partially dissociates in water. So there's an equilibrium between carbonic acid and hydrogen ion and bicarbonate ion. You may be familiar with sodium bicarbonate, which is baking soda. So that is a weak acid and base there. So for number 9, which of these beakers contains a basic solution? I'll give you a moment to think about that. If you want to pause, you can pause as well. But if we look at these solutions, if we're looking for a basic solution, it should have less free hydrogen available. So this second beaker is our basic solution. This first beaker here, it's got an equal amount of hydrogens and OHs, so this one's neutral. And then that last beaker, right? This one has more hydrogens than OHs, so this one is acidic. Okay, we're typing in. Sorry, my Boston Terrier, if you can hear her snoring in the background. She's an old lady. You got to give her some grace. So then what's something that would be hydrophobic? Hydrophobic. What's that mean again? Hydrophobic, it means it doesn't dissolve readily in water. So something like oil would be hydrophobic. So that's it. We made it to the end of chapter 2. So we talked about the molecular formula. So that just shows us how many atoms of each particular element are in a molecule. So like H2O has 2 hydrogens and 1 oxygen. 3 subatomic particles. We got protons. What's the charge of a proton? Positive. Neutrons. What's the charge of a neutron? Neutral. Electron. Charge. Negative, right? What's in the nucleus of the atom? That would be protons and neutrons. What's an isotope? It's atoms of an element that have different numbers of neutrons. With electron shells, how many electrons can the first shell hold? 2. Second and third shell, 8. Or up to 8, right? Periodic table is arranged to show electron distribution. What's the whole number on the periodic table represent? How many protons are in the nucleus of that particular element? With chemical bonds, we've got ionic bonds, covalent, and hydrogen bonds. What's happening in ionic bonds? That's transfer of electrons, or you could also say attraction between a cation and an anion. What's the charge of a cation? Put your paws up, it's positive, right? Cation's positive charge, anion negative charge. So ionic bonds could either be described as transfer of electrons or attraction between cation and anion. What's happening in covalent bonds? Root word co means together, sharing, right? So they're sharing valence shell electrons. And then hydrogen bonds are a weak association between a partially positive hydrogen and another partially negative atom. With chemical reactions, reactants are what go in, products are what come out. Things that can influence the rate of chemical reactions: if we increase temperature, that increases rate. If we decrease particle size, that increases rate. If we increase concentration, that increases rate. If we add a catalyst, that increases rate. With polar molecules can be polar because the entire molecule has a partially negative end and a partially positive end. This happens due to distribution of electrons and shape of the molecule itself. Properties of water: water heats up and cools down slowly. Ice floats. Water makes a good solvent. Solutions: so water would be the solvent of life in most cases, right? And then a solute would be something like salt or sugar, and then the salt or sugar in the water together makes up the solution. Something is hydrophobic if it does not dissolve in water. It's hydrophilic if it does dissolve in water. pH is a measure of the concentration of hydrogen ion in solution. Acids have a low pH, bases have a high pH, and buffers help reduce pH change. And that's it. We made it through chapter 2. Look at us go.